Welcome back. So we have been looking at how to count the cardinality of sets. So this is what we call as combinatorics, so which is a branch of sub-math that involves counting. So most of the time the typical question is, given a set S, what is the cardinality of S, or in other words, what is the size of the set S, or how many elements are there in the set S. Now, the question to be asked is that, how is this set given? And most of the time, when we talk about this kind of problem, we say that the set is given implicitly. It's not given explicitly. It has been described. For example, it can be something like how many elements of a particular universe set satisfy certain conditions. Or equivalently put, how many ways can you draw an element from the set such that the element satisfies a set of conditions. Now we have some problems that we should keep in our mind before we what we should like to solve. The first one being, how many n-digit numbers are there in decimal representation with no consecutive digits same. The second, how many functions are there from the set 1 to n to 1 to k that are not decreasing. The third, how many ways to distribute n identical toffees among k kids. And the last one is the number of 0-1 string of length n which does not have any consecutive 0. Now, the question is that how to count is an extremely challenging problem. Every problem, every set that we have to count has its own complications and should be tackled differently. Even some of the greats of math like Srinivasa Ramanujan has worked on counting for quite a big part of his life. And here in these few lectures, we will be giving some tricks and tools which will help you to attack problems. But again, as I tell in every class, you should use your creative mind to understand which problem can be solved using which trick. Every problem is different. Every problem is unique. Now, till now we have already looked at this problem of how many ways can I select k objects from n objects. And we have looked at the two cases, namely what happens whether are we allowed to pick a same object multiple times, meaning is repetition allowed among the k selected objects, and is the ordering of the objects in this k objects matter. And we have seen how to solve in all the four cases. The next one that we looked at was how many ways can we distribute n balls into k beans. And there are few cases to be studied, particularly whether the beans are distinguishable or not, whether the balls are distinguishable or not. If the balls are distinguishable, is the ordering in the bins matter? Can the bins be empty? And is there any other restrictions that can be asked? And in the last video, we looked at this problem and we solved some of the parts of this problem. Namely, we did solve the case when the bins are labeled and items are indistinguishable. And in case bins are labeled but bins can be empty, we also solved when the items are distinguishable and ordering matters or doesn't matter. In either case we solved that. But we were left with two of the problems which we will be tackling in this video, namely, if bins are labeled but cannot be empty, then how do you solve it? And also we were left with the case when bins are unlabeled. Now, before we start working on those two things, let's do a little bit of study of the theory behind it. The important thing is that, so if A and B are two sets, and size of A is P and size of B is Q, what is the size of A union B? Note that this is very similar to the additive law that we studied two videos ago. It told that if A and B doesn't have anything in common, or in other words, what it told was that if A intersection B is empty, meaning if the cardinality of this one is 0, then the cardinality of A union B, meaning whether either A happens or B happens, is P plus Q. But what happens if this is not 0? For example, if I have this is as a set, so if this is the universal set where we are working on, if this is A and this is B, this is A, this is B, and A intersection P does have some place here, how do you solve it? Now, as you can see from the picture in some sense, what happens if I look at size of A plus size of B? So in the case that, okay, let me just complete this line, size of B is this set and A is this set. Now note that every point here inside A union B has been selected once if it is somewhere here and once if it is somewhere here, but if it is in the intersection, it has been counted twice, right? So it's like if you have to place two round paper cuts one over the other, you need to cut away, once you cut away this chunk out once. So if you subtract A intersection B, you should be getting A union B. And that is a very crucial thing, that A union B is size of A plus size of B minus the intersection of A and B. Now, so what is the answer? Answer is of course that A union B is size of A plus size of B minus A union intersection B. Now what happens if I have three sets? So we're back to the same Venn diagram for sets that we always look at for such kind of situations. If you have A, B and C, then you can first pick up all of them, you can first cover all of them, but then say this is A, so this is B, and this is C. Now as you can see that the space of A intersection C has been counted twice, first by A and then by C. So I need to subtract at least one of them away, right? So I subtract A intersection C. I also have to similarly subtract A intersection B, and I have to subtract A intersection B I have to subtract B intersection C. Now what happens in this case of this small area? This was counted once for A, once by B, once by C. It was subtracted once by A intersection C, subtracted once by intersection B, subtracted once by AB intersection C. That means right now this one has not contributed anything. So I need to now add it up. So I have to add this part, A intersection B intersection C. So in other words, what I will get is that I will get that A union B union C is equal to first adding the sets individually, then subtracting the pairwise intersection, then adding the three-wise intersection. Now question is that what happens in the case of fourth case? If I have four sets A, B, C, D, in that case what is the size of A union B union C union D? Is there a formula for it? And we do have one, and that is called the principle of inclusion exclusion. And it basically talks about that if I have n sets A1 to An, then what is the size of A1 union A2 union till An? So the size of the union is first add the individual sets, then subtract all the pairs of intersections, then add all the triple intersections, then subtract all the fourth intersections. So in some sense you are adding, subtracting, and you keep on going on till the last one where you add or subtract depending on what is the size of n. If n is odd or even, it's minus 1 power n plus 1, you add or subtract the intersection of all the sets. Now this is a theorem. I'm not going to prove this theorem. I leave this to you guys to check that this theorem is indeed correct. You can prove this theorem using induction. But this particular theorem is an extremely powerful tool for counting. So writing it in a nice way, we do get this particular expression. So once we have this principle of inclusion exclusion, we can use it to solve many of our problems. So let's start with this problem when we say that there are n constables in your police station. You want to divide it into 4 projects: project 1, project 2, project 3, project 4. No constable can be part of one project, more than one project, and every constable should be part of some project. And also at least one constable should be assigned to every project. So none of the projects should be empty. Now how do you solve it? If you remember, if we don't have this particular thing that every project has at least one constable assigned, then we saw that the first constable can be put in either of the 4 projects, the second constable can be put in either of the 4 projects, and so on. So the total number of ways of assigning the constable in the 4 projects is 4 power n, right? But here, unfortunately, it's the possibility that some of the projects might be empty. So we need to get rid of them. If you want to ensure that every project has some constable, then we have to subtract all the possible. So subtract all distributions where at least one project is empty. Now how do you do it? So let me define this new class AI. AI is the set of all distributions meaning of n constables into projects where project I is empty or it doesn't have any constable. Now if I have defined this AI in this way, then how do I define the set of all distributions that are empty? So set of all distributions that are empty is nothing but union over AI, or rather in this case it will be A1, all the distributions where the first project is empty, or all the distributions where the second project is empty, or all the distributions where the third project is empty, or all the distributions where the fourth project is empty, and you abstract them out, right? So we can now subtract. So this is the set of all assignments or all distribution of constables into 4 projects where some of or at least one of the project is empty. And when I subtract that one from 4 power n, I get my required answer. Now by the principle of inclusion-exclusion, I can write this one as, so all I have to do is that I have to write this particular term, right? The unions. So let me just, don't worry about this one. Now what is this term? This is summation of A1 plus A2 plus A3 plus A4. Now what is A1 plus A2 plus A3 plus A4? What is A1? A1 is the number of ways in which the ith project is empty. That means nobody goes to the ith project. How many such ways can you distribute n constable into 4 projects where the first project is empty? That means it is same way as distributing n constable into the project 2, 3 and 4. So this one is equals to 3 power n. First constable can go to project 2 or 3 or 4. Similarly, this is also 3 power n and 3 power n. Now, by principle of inclusion and exclusion, I have to subtract A1 intersection A2. I have to subtract A2 intersection A3 and so on. Now, what is A1 intersection A2? A1 intersection A2 is the set of all distributions where the first and the second project are empty, right? And this can of course happen with both the projects are empty. That means it is same as dividing n constable into only project 3 and project 4, which is 2 power n, and all of them are same. And similarly, when we have to do it for A1 intersection A2 intersection A3, these are the number of distributions where project 1, project 2 and project 3 are all empty. And this can only happen with one way, where all of them goes to project 4 and so on. Note that this is what, so the main idea is that intersection of AIs can be sometimes very easy to compute, as in this case. And if intersection of AIs are easy to compute, then by the principle of inclusion and exclusion, I can write the cardinality of the union of the sets. And by doing so, we can get the number. Now, it will not be a very compact number, but it is still something which has a expression. So, in fact, we can write down the expression of that exactly. So, if there are n objects, n distinguishable balls and k labeled beans, how many ways can you place the n balls in k bins when ordering inside the bin does not matter, but no bins can be left empty? It is k power n minus this way. Now why this k choose I? Because k choose I is the number of ways in which I can choose I of these sets and take intersection of them. Right? I have to, for example, this should be like k power n minus intersection of all the a1, a2s, right? So all the a1, a2 is k choose 2 times k minus 1 power n plus all the triples k choose 3 and all the triples, the value in ai intersection aj intersection ak is k minus 2 power n and so on. So this gives us a kind of a closed form expression, not exactly a closed form expression, but an expression of this kind for getting the number of ways in distributing n balls into k bins with no empty bin. So we can use the same technique when the ranking inside the bins matter. If you remember, ranking inside the bin without when the empty bins were allowed was this one, and now we can do the same, identically same thing with the principle of inclusion exclusion, and we can get this term. So by doing so, we have been able to fill up this particular matrix. Now let's try to see if we can solve the other three possibilities, namely when bins are unlabeled. Now when bins are unlabeled, for example, this is a typical example when you have to divide the constables into 4 groups and we don't care about which group is assigned to which project. How many ways can you do it? Now the idea is that if I say assign constable C1, C2, C3 to project 1 and C4 to project 2 and C5 to project 3 and C6, C7 to project 4, note that if I permute this project 1 to project, if we don't have any name for the projects, in that case, if I change the project ordering, say P2, P3, P1, P4, any of the ordering are equivalent and they would have been counted in when we didn't take care of the fact that they are not indistinguishable. So by using this technique of the equivalence classes, we can see that every distribution with the labeled projects belongs to an equivalence class of the same size, namely the number of ways you can permute these 4 things, which is 4 factorial. So by the technique of this equivalence partitioning, we can now just divide. So if I have to solve this thing of the k distinguishable balls into n indistinguishable ball to k unlabeled bins, we have to take in the case when I have exactly k bins that are filled, no empty, and I divide it by k factorial and I get the answer. Note that if I had not taken the number here when everything was empty, when they were not empty, then things could have been a bit more weird. So by the same argument, by the way, this particular number, so this is the number of ways in which one can distribute n distinguishable balls into k unlabeled bins when the ordering in the bins does not matter, but no bins can be left empty. This is called the Stirling number of second kind, denoted by Snk. Similarly, we can do it for the third, for the last of this thing of, which is when ordering inside matters doesn't matter and bins are unlabeled. Now with this we have done basically all the cases except this case, namely when items are indistinguishable and bins are unlabeled. How many ways can you do it? Now this is a very hard problem and we will be talking about this problem in the next video. Thank you.